Um, Let us first briefly recap what we've learned yesterday. I'll try to use this. Okay, okay. So last time we introduced quantum LDPC codes, yes, and they're defined by a pair of matrices. So we define their dimension as the dimension of the coset, yes, and we view these codes as a cosets. And we also defined its distance, which is also sometimes is called quotient Hamming distance or systolic distance, which is just the distance between different cosets. And so they're interesting for possible future fault-tolerant quantum computers. And as you can see, so we can view them as a generalization of a classical LDPC code. And so we can represent them since in the classical LDPC code, we have just one matrix. Here we have two matrices, and we can also represent them by a kind of Tanner graph. But in this Tanner graph, yes, we have three parts. The middle part corresponds to qubits, and we have two types of checks. And as usual, yes, so as I said, the dimension is just, so you can think about it just the number of qubits minus the number of all checks. Of course, we do not count, there are some checks that are dependent, yes, and so we just count independent checks. Okay. Then what we discussed next, that so in fact, the most natural thing to do, where can we find all these codes? So we can find them in topology, and topologists knew how to construct similar objects long before quantum LDPC codes were invented. And the standard approach now is just to take some topological space, convert it in a quantum LDPC code. And I showed you last time one of such an examples, the famous Kitaev toric code. And so I mentioned the parameters here. So here we have three parts, yes, faces, our squares, our edges and vertices, and we have a natural linear maps between them. And if we represent it as a Tanner graph, you can see that it has very natural and regular structure. Yes, so it's and that is why these codes are so popular, because physicists really like this 2D layout, and so they're really promising in practical quantum computers. Okay, and what we discussed next was tensor product codes, and so if you remember, yes, we just consider a set of matrices, every row from the code A, every column from the code A, every row from the code B, and so we naturally can also describe this as a set of, as I said, set of matrices that satisfy these two conditions. Yes, we multiply from the left by the matrix A. It means that we multiply each column by this linear map A. Yes, and if we get 0, then we check that every column is from code A. And we do the same for the row code. And what is known about this tensor product code, that they have very, very nice parameters. Yes, so this one is trivial. This one requires a little bit of linear algebra since it's a tensor product. Yes, we know from linear algebra that the dimension is given by this formula. But for the distance, it is also quite trivial. Yes, just if you consider any non-zero code word, it should be a non-zero code word from code A, which means that in this row, we have at least dA non-zero elements. And then for each non-zero element in this row, we also have in the corresponding rows dB non-zero elements. Then in total, we have at least dA dB elements. And it is an easy exercise to show an example that achieves this bound. So this is pretty trivial and well known. Okay, then we switch to hypergraph product codes, which kind of two-dimensional analog of tensor product codes. And to see this, we just need to look at the syndromes of the tensor product codes, yes, as I described it before. So, this is a syndromes, U and V, and if U and V are equal to 0, yes, if you multiply by matrix A, matrix B, and we got 0 matrices here, then we check that this is indeed a valid code word from the tensor product code. And what we showed last time, that this tensor product code has a lot of dependencies, which is of course very convenient for applications for locally testable codes. And if you look in the past, so there were a lot of great work that consider these tensor product codes in this context. And this is exactly because they have a lot of dependencies. And these dependencies are shown here. So we just multiply U and V by the corresponding matrices A and B. And we show, due to this associativity of the, in fact, this of course works not only with fields, also with rings. There is no, so it's a universal idea. And it implies that we have this relation between U and V. Yes, they should satisfy this relation, which means that we have a lot of dependencies. And the number of dependencies is captured by the size of this matrix, of course. Okay, great. And here, so I showed you the chain complex that we can construct out of this idea. Yes, so we first start with this matrix. These are our this our like two-dimensional object. We apply this, calculate these syndromes, and then this checks that the syndromes satisfy this condition. And as you can see, this is exactly the chain complex, and which means that we can consider the corresponding homology groups. Yes, previously I thought that so these quotients are called homology groups. And so if we consider the quotient for this layer, yes, for this U and V, this is exactly the hypergraph product code. And by the way, originally, if you look at the paper by Tillich and Zemmour, you can see that they define it in a little bit different way, but you can easily check that this is exactly equivalent. So this multiplication by matrix A, matrix B, just like a tensor product operations. And so you can easily show that this is exactly the same. Okay, and what is also interesting that the homology group that corresponds to this layer, yes, here we assume that we have 0, we had some additional 0 space, and the boundaries of this space are 0. And which means that homology groups just exactly the same as a kernel, yes, as a kernel of this linear transform. So this is, so the homology group is exactly the tensor product code. So which means that this tensor, so this chain complex, it gives simultaneously you hypergraph product codes and tensor product codes, which is really nice. Okay. And when people consider hypergraph product codes, they usually, and there was a question even yesterday about it, how we get some dimension, non-zero dimension. And the trick here is as follows. So we just, instead of B, so here we had previously B transposed, but we changed B by B transposed. And in this sense, so we get, so this is exactly the same code, yes, but we just changed this matrix. And as you can see, after that, we even have much more symmetric chain complex, yes, even more symmetric conditions that describe this chain complex. And now the trick is just to calculate the number of checks here and the number of, so here we have X checks and Z checks. We just calculate them, and they show that the number of checks is smaller than the number of these qubits. That's a very easy trick. And this shows that this code has a constant rate. So it's very simple. And Tillich and Zimmer show that this gives us, so if we use this, so if we choose some linear code and we choose some full rank parity check matrix H, they show that this construction gives you a code with this parameter. So n squared, m squared, this is these two matrices. This is a length. K squared is obtained if you just substitute from n squared and m squared the number of checks here. You can easily verify this. And D, it's a little bit tricky. I will tell about it. So it can also be shown that the minimum distance is equal to D. And now, how can we use this idea to construct LDPC code? We also need LDPC codes. Yes, we are not just interested in dense codes. And since we all know that there exists good classical LDPC codes, we can just substitute them, and you can easily, again, verify that these parity check matrices, yes, that corresponds to this linear maps, they are sparse, since the matrices A and B are sparse. So this is trivial. So this is indeed LDPC code, and it has, as you can check, the parameters shown in here. I also want to mention, and I gave it as an exercise last time, that toric code that we described before is a special case of this construction. And can anyone say me what code I should substitute to this construction to get toric codes? Repetition code, exactly. And we can use, and by the way, so repetition code has two types of parity check matrices, yes? And this is a little bit tricky part. So if we use standard cyclic parity check matrix, then we get what is called toric code. But we can also use without parity check matrix without the last row, yes, because we do not need last row. And in this case, we get what is called surface code. And surface code is a little bit more convenient for practical applications because it doesn't have these boundary conditions. Okay. And so the natural question is, of course, can we generalize this idea of hypergraph for the codes to get quantum LDPC codes with better parameters? And the answer now is known, so we can do this. But so before let me just first summarize what we've learned about chain complexes. Yes, because I think I didn't give the full formal definition. What is a chain complex? So a chain complex is just a collection of, so chain complexes just generalize the CSS code that we saw, yes? And this is just a collection of vector spaces. So we can view these vector spaces as just registers of bits, for example. And we have this like matrices, yes, linear maps between the spaces. And we can interpret this either as generator matrix or parity check matrix. So we have two interpretations here. And so we require that we have this condition for all I. And formally, it is convenient to consider this chain complex as an infinite. This is just much easier, so we do not need to deal with edge cases. And so how we get what we need? So we just add zero-dimensional spaces here and zero-dimensional spaces here. And in that case, so we get like bounded chain complex that have only finite number of non-zero elements. And for example, classical LDPC codes is a chain complex that involves two spaces. Yes, quantum involves three spaces, and etc. So we can generalize this. And so we also already mentioned this. So we call the images of this map. Yes, we call it I boundaries. So this is the images of this linear map. This is what we also call degenerate code words, yes? And here we have cycles. This is a kernel. This is the elements that satisfy this parity check matrix. This is what boundaries is what we generate with this generator matrix. And cycles is what we check, yes, to be a code word by this parity check matrix. And we have, since we have this condition everywhere, so we have this condition between these two spaces, and this condition, of course, give us opportunity to define this quotient. And this quotient is exactly what corresponds to CSS codes, as you remember, and it is called ith homology group. And as I also showed, yes, for CSS codes, we have one direction, but we are also interested in other direction. And this other direction, so we just transpose all the matrices and reverse the arrows. And we also can get a chain complex, but in this case, so we have a little bit different indexes, and it is usually called co-chain complex. And we we add co to all these names: co-homology group, co-boundaries, co-cycles, and everywhere co. Okay. And of course, our famous example of toric code, yes? So we have all these guys here. And they are homology groups, as we've learned, yes, toric code has dimension 2, which means that this homology group that corresponds to this layer, its dimension is equal to 2. Okay, but let me also a little bit generalize this. Yes, what we learned before, it was an example of a tensor product of chain complexes. So we can do with chain complexes some different operations. Yes, if we have two chain complexes, A and B, we can give a tensor product out of them. And idea is very simple. Yes, so we have chain complex that goes vertically. We have chain complex B that goes horizontally, and we just multiply each term here on each term here. So if, for example, this has m terms, this has n terms, and we get m by n terms, yes? And so when we multiply them, so we get the set of matrices, and we also define this tensor products. And this tensor products by exactly the same what I described before. Yes, we apply a linear transform to every column and every row. And this is just a formal way how you can describe it. And how we also define the layer. So we define the layer, yes. So we just calculate the dimensions. And if the dimensions sum up to k, yes, so we call it, yes, so this corresponds to the layer k. Okay, and these things were very well studied in algebraic topology, and in fact, it is known that they correspond to, homology groups are used by topologists to study topological spaces, yes? And so to each topological space, we can assign these homology groups, and if two spaces are homeomorphic, then they have the same homology groups. And what is known that if you take the tensor, the Cartesian product of two topological space, then the homology group that corresponds to this Cartesian product, it exactly corresponds to this tensor product, if we consider it over a field. So here, and today and yesterday, I'm talking about finite field of two elements mostly. Okay. And by the way, so if we apply this idea to graphs, yes, Cartesian product. And so we get what is called square complex. So we have vertices, edges, yes, multiplied by vertices, edges. So we got also vertices, edges, but we also get squares when we multiply this edge by edge, yes? And so this full space It's a Cartesian product, but we can also remove these squares, yes, and we get a graph, just a standard graph. And this graph is also very well known in graph theory, and it is called Cartesian product of graphs. You can easily check in Wikipedia its definition, but it's trivial. And what is interesting, why I mentioned it, because if we consider, we can interpret the hypergraph product codes in the following way. So we have one code that's defined by matrix A, and to this matrix A, we have some tenor graph, yes? And we have another code defined by code B, and it also has tenor graph. And the tenor graph of the quantum code obtained by hypergraph product codes is exactly the Cartesian product of these graphs. And this is why, let me, okay, let me move to here. I showed it. Okay, and this is exactly why we get this layout here, yes? Because we have one cycle that corresponds to the repetition code. We have another cycle that corresponds to repetition codes. And this is exactly the Cartesian, sometimes it is also called box product. Okay, yeah?
Formulas for the tensor product look very similar to like a multiply polynomial.
Yeah, exactly. This is just, yes, this.
Boundary is sort of like derivative of product.
It's like derivatives, this, exactly. I think, yes, there are some deeper connections, but I'm sure that they are not used to construct this. Yeah, yes, of course. This is something that this formula should look familiar to you, yes?
Even the CK looks like a quantity.
Yeah, and yeah, so of course, so we can consider it like a product of two polynomials. So yeah, and by the way, there's also some Gilbert polynomials associated to chain complexes, and yes, there are some deep connections between here. But let us. Sorry. Yeah, SK1 is just one skeleton. It means that we just remove all objects that has dimension more than one. Yes, so if we have some weird cell complex that consists of some cells of different dimensions, and if we just remove all cells of dimension more than one, we got graph, and this graph is called one skeleton or underground graph. So Max already underlying graph, yes, underlying graph. So this is the same thing, yes. Yeah.
CSS code standard graph is the hypergraph product, but the CSS code is specifically.
Yeah, CSS codes is defined by two tenor graphs, yes, and you mean this?
Yeah. You said the code and take the tenor graph, and the CSS code standard graph is the product of those two graphs.
Yeah.
The CSS code has two tenor graphs.
Yes, but look at this first picture from my first slide, very first slide. Every CSS code is defined by three-partited graph, and this is still a graph. And when I talk about Cartesian product, so I took Cartesian product of two such graphs, and I got a new graph, which is this graph. So you also need to define which of the vertices would be X-checks, which would be qubits, and so, but as a graph, it is a Cartesian product, which is, I think, is very important to understand. Okay. So how much time do I have? Still, so 35-40 minutes, okay. Okay, great. Let us discuss a little bit more about this distance bounds and some dimension of the hypergraph product code. So here I show you the definition, yes, of this complex. And first of all, let me also introduce some additional notation. Let us denote by Ka the dimension by of the code A, and by key A transpose the dimension of the transpose code. Yes, which we talked about last time a lot. And we also have the same or B. Okay. And the reason I introduced this notation is because we have the following general formula. So before that, I only showed you what is the dimension of hypergraph product code only in some special case. Yes, that was the main case in the paper, hypergraph product code. But in fact, you can also give the dimension in the more general case. So it is given by the following interesting formula, which is also was very well known before, even before hypergraph product codes were introduced. Yes, it was rediscovered, and it is known as a Kueneth formula. And let me so it's, to be more precise, it's a special case of the Kueneth formula. Okay. So the Kueneth formula, it just gives you the dimension of the tensor product in terms of the homologies of the chain complexes. Okay. This is a dimension of this tensor product of these two vector spaces. And why it is just a special case, it's quite easy to see. So if we consider, yes, this code, an A, for example, an A given by the matrix A, then if we consider it as a chain complex, yes, we have here zeros, and we also have zeros here. So what's the homology? What's the dimension of the homology group here? So here we have zero boundaries, yes, and we have the kernel, and which means that this H. So let us call it. So this is the first homology, yes. So the first homology is equal to key A, yes? And the same if we consider, look here. So here we have zero here, but here we have also image of the matrix A. But using, but if you reverse the arrows, yes? So if we calculate the cohomology, what is called cohomology, and from CSS codes, we know that yes, homology is the same, yes? when we defined CSS code, we defined it as two possible cosets, yes? And in both cases, the dimension is the same. And the same is here. So the dimension of this cohomology or homology, H0, is equal to key A transpose. Because when we transpose here, we can see the transpose matrix. And we have 0 here, so we have 0 boundaries. And we have the kernel of transpose matrix. So this is related to co-kernel. If you know from linear algebra, there's a notion of co-kernel. Okay, so, and the same thing for B, yes, of course. And you can easily check that this formula is just an instance of this Kunis formula. Okay, let us show that it is true. And in order to show this, so we need some additional concept that is also, I think, many of you heard about this, it's an Euler characteristic. So if we have a chain complex, for example, the general chain complex, okay. These are boundary operators. Yeah, this is boundary operators. I just denote co-boundary as transposed of this. Okay, yes, it's different people here, some use. So what is important, you need to use index either, if you use index below, then it's chain complex. Okay, and how we define the Euler characteristic? So it is defined in the following way. So it's just -1. Okay, so it's very simple. And what is known about this Euler characteristic, why it's so important? So it is independent, so it's also invariant, yes? As you learn from maybe even from school. So there is a famous formula, yes, for this, and for polyhedrals. And in fact, the following is true. So you can also show that this characteristic can be calculated using homologies, not just dimension of these vector spaces, but by using dimensions of homologies. And how to see this? It's very simple. So so each homology group, dimension of homology group is just like dimension of CSS code, yes, in the level E. And what is the formula for CSS codes? Yes, it's just the number of qubits, which is dim as Sy, minus ranks of the two parity check matrices, Hx and Hz. Okay. And here we can see that these guys cancel. Yes, because when we calculate this, yes, and here it's quite convenient that we do all the sums over all possible integers, yes, and you can see that these guys cancel. You can easily check this just by calculating the Euler characteristic from for example, just for linear code. And by the way, what is the Euler characteristic? Just for the code defined by the matrix A. Let us show this. Okay, so here we have some chain complex. Okay. What's the Euler characteristic of this? Okay, by definition, it is MA minus NA, yes? Because here dimension 1, here dimension 0, yes? Okay, but at the same time, by this formula, it is also equal to K A transposed minus EA, because K A transposed is this homology, and K A is the dimension of this homology. And you can easily check that this is again true, yes? You just by using these ranks of the matrix A. You can see that this rank cancels, yeah, and this formula can be easily checked. Okay, and we had the same for B. And what if we multiply all this together? Yes? If we multiply this, you can see that we get the following. So here we have K A transposed by K B transposed plus K A plus K B and minus K A K B transposed plus K A transposed multiplied by K B. Now another fact that you can again easily check just from definition of chain complexes, that K A tensor product B is equal to what? Can anyone guess? It's just a product. Yes, you can see this just from the definition of the tensor product of chain complexes. Yes, how we define them. Okay, and so here we can replace it by K A B. And what we get right now, let us interpret these guys, this term. K A by K B. So this is a homology of this part, yes? This is a dimension of the tensor product code. So this is a homology H. Now in our notations, yes, it's the homology of dimension of H2. No, this is H0, but here it's H2. So here we have the dimension of this homology, because it's, as we've learned, this is exactly the kernel of these two matrices, yes? So it's tensor product code. And the same here, yes? What's this term? This term It's a tensor product of two. Now we can see the cohomology. So we can see the reverse arrows, yes? And we calculate the dimension of this. So we consider the kernel of these reverse matrices. And we get this formula, Ka by Kb. And what we have here we have just so here we have the following formula. Using this formula, yes, we can write this as dimension of H2 minus dimension of H1 plus dimension of H0. And what we see right now, this corresponds to this corresponds to this, but this should correspond to this. That's all. Okay. And in fact, you can also prove some by similar methods a little bit. The proof is a little bit more involved for the general case, but at least we need right now this formula. And now how we can use this formula, why it is so important? Because it's not just give you the dimension, it also gives you a way how you can estimate the minimum distance of a hypergraph product code. And why that? Okay, let us estimate the distance. Okay, let us consider the case, for simplicity, consider the case of the original paper on hypergraph product codes, yes? So we have two matrices, and we have the dimension, we have the distance of this is equal to D. How we can prove that this D is indeed a distance of this code? First of all, let us give an example that achieves this D. Can anyone give me this example? Can anyone see how we can get this example? So we need an example of a code word, two matrices U and V, such that their syndrome, yes, they satisfy this condition, but we cannot obtain them as boundaries. Yes? So what an example of a code word of weight D we can. So in this case, yes. Okay, so for example, yes, here we can get weight D, yes? Mm-hmm. For example, yes, we can place any code word of weight D here, yes? It gives zero syndrome, but here we can just put zeros. And you cannot obtain this because here you have, so you cannot, so this matrix should be zero. Yes, because in order to obtain zero, so it's at least in one of the dimensions, because we have H1, H and H transpose, yes, one of these guys, so you cannot obtain them because you have, so in order to obtain this code word, you need to use V equal to 0, and which means that this is non-degenerate code word. Okay, but how we can prove that we do not have smaller code words? And here is exactly when we need this Kueneth formula. So the idea is very simple. We just consider some code word, some non-zero code word here. And we just look at the rows and columns. Here and here. For example, here is I, indices I that cover all non-zero elements here, but here indices J that cover all non-zero elements here. And by assumption, so we have I and G both smaller than D, yes? Okay, great. And now what we consider what is called a subcomplex. So we consider new complex. That is, so we remove all these guys. Yeah, so let me just show what we, not what we remove, or what we have in this complex. Okay, so this is a new chain complex. And now if we apply this formula to this chain complex, we can see that it has 0 dimension. Why is that? So this is, let me write it formally. So dimension of hypergraph product code is A. So we restricted it to J, and B restricted to I is 0. This is because these matrices A and B, yes, this parity check matrix of a code that do not have non-zero code worth smaller than D, which means that these matrices, yes, when we restrict them, one of the dimensions, either key A or key B, so one of the dimensions, so key A and key B, in fact both, would be 0. And which means that by this formula, we have 0. Key A equal to 0 and key B equal to 0. And what it means for us? It means for us that there exists such matrix that if we apply the matrix B, that gives you exactly this and this. Yes, because it has dimension 0, which means that every code word is a boundary. Then it means that for this code word, particular code word, we have some W that gives you. And which means that this can also be done in the full complex. And this proves that dx distance is at least D. And we showed an example when it is again D. And you can do it in the different directions, because for quantum code we need a different direction, and the proof is exactly the same. So we just reverse A and B. Mm-hmm.
And everything else is.
Yeah.
What's the corresponding?
So you mean what are examples of non-trivial code words? Oh, okay, the example was also already given. So here we choose a code word of weight D, and all other code words are zeros. And here all zeros, all zeros. And we cannot get this because so this matrix, so we cannot, if matrix H is full rank, then yes, in order to get 0, we need also here 0. And so we cannot reduce this. Okay. A natural question is whether we can generalize this, all this, yes. And let me switch to my presentation. How much time do I have? Okay, great. Is everything clear? So do you have some maybe questions? Or... Okay. you can do it without this, but so it simplifies, so it justifies this formula because we use it here. So it's Euler characteristic. Yes, so we use it here. It's Euler characteristic of this A and B. And we also, and it also explains why we in the first place should consider all this. Of course, yes, you can just prove this. And in fact, in the paper by Tillich and Zemmour, they didn't use any Euler characteristics, just substitute these formulas. And I always was fascinated, what is this all about? Because it just magically happens that this is everything true. But then I found some explanation for this. So it's just one of the possible ways how to show this. Nothing special. Okay, and last time I also mentioned this idea of graph lifts, if you remember, yes? And we can apply it to classical codes. And so the natural question to ask, since for classical codes, this idea works great if we consider arbitrary permutations. I showed you before the results that show that if you use arbitrary permutations, then this lifted code that obtained by these lifts, yes, has the parameter that grows with the lift size linearly. And by the way, the dimension of this code also grows linearly, but this is trivial because we just have proportional number of checks and bits. So why this? This is one of the reasons why these lifted codes are so popular in practice, because you can guarantee some dimension. And the natural question to ask whether we can do something similar with quantum code. Yes, we start with this quantum code. Maybe we can also lift it, and maybe we can also hope that we have this. And in fact, this really happens. And there are many possible ways how you can formally, yes, define this lift. So you can use, as you maybe saw in the literature, and I will tell a little bit more about this later. So we have different ways how we can describe. We can describe it either by just by lift, or just using what is called balanced product or twisted product. So there are many different ways how you can describe this one object. So here, this idea, and we just apply. So what if we just take these two lifted codes, as I showed previously, they can be described as codes over ring, yes? And the simple idea is just let us instantiate this idea of the hypergraph product codes, but instead of the field where we have only one bit, consider them as codes over ring, yes? And this is exactly the hypergraph product codes, yes? We do not change any of the definitions. So this is just non-binary hypergraph product codes over a ring. And what is interesting, that we can also use this for classical codes, yes? And by the way, these codes are not very well studied. So they were studied a little bit before us, but not so very well studied. So this is just a tensor product code, but here symbols are these group elements. And what we get, we can easily show that we get good classical DPC codes, and it's trivial. Why it's trivial? So we have dimension. Dimension, we just calculate the number of checks, yes? And compare to the length of the code. So we can ensure linear dimension. But linear distance is also trivial, yes? And how we show it? Exactly in the same way as for classical tensor product codes. Yes, suppose we have here some non-zero elements, which means that if we have non-zero elements, then we have some number of blocks that are non-zero, yes? And then, so if we instantiate codes with linear distance, then we also have some number of blocks that are non-zero, and also, which means that we also have some number of blocks of rows that are also non-zero. And then you can see that which means that we have at least one row or column which is non-zero and which is a code word. And this means that it has linear distance. So this is also a very simple example of classical good LDPC codes. But we are interested, first of all, in quantum codes. And by the way, the code by Dinur, etc., is not exactly this. So it doesn't have this particular structure, but is very close. So it can also be considered kind of tensor product of two codes. And here, so this is a quantum code. It's like non-binary version of hypergraph product codes, and we do not change any definitions. Exactly, everything is exactly the same, just substitute different elements in the parity check matrices. And the natural question is, can we do this? And unfortunately, if we try to apply this idea in the same way as the hypergraph product codes, yes? So it's very natural to assume that since for tensor product codes, we have this formula, yes? We should expect also very good results if we just take the idea of original hypergraph product codes, yes? And consider a code with a good code with a parity check matrix H, and then transpose it. And quite, yes.
About the tensor example.
Okay.
Yesterday we said if we look at if according to a cyclic group, we get constant.
Yeah, exactly. Here group is arbitrary, so it's
Sample for the thing on the top is not the actual.
But by the way, even for so what I showed yesterday is that if we take some fixed graph and we lift it, then yes, we get constant distance. But if this base graph grows a little bit, like logarithm, then we can get linear distance. Yes, this can also be shown. So the situation is not that bad even for abelian groups. Okay. And what is really amazing that this idea doesn't work like that. And the easiest way to see this is just give an example of, maybe I can remove this. Okay. Here we replace, so we can see the LPH, HT, yes, and how it is defined. It is, in fact, the set of U and V that satisfy these relations, U So this is our boundaries, this is our cycles. And this is because I substitute H transpose, yes? So you can, yeah?
Tensor of the ring tensor of the n denoting two things over there, n is both the size of the group algebra as well as the block length of the classical code that is being
Mm-hmm. So the classical code has length, has length of the total number of these bits. So for each group element, yes, we count the number of bits here, here, here. So this we should all put them in one large code word. But here. Okay. Yeah. But in bits, here in bits, yes? Okay. yeah, n here is equal to n by size of the group. So n and the length of the code is just the number of these group elements, yes, multiplied by the group size. So the group size, of course, also so
because the line above says the group n.
group size. Yes, the group size is indeed. So we use. So this is constant. N is constant. So I assume that n is constant, and which means that the group size grows as n. So we have just constant number of these blocks, and this is crucial, of course, to show this. Okay, and what we see right here. Okay, what we see right here. Let us switch to the Blackboard. We see that, in fact, you can easily check that this, so we can give an example. Maybe someone can even guess what is this example of a non-degenerate code word. So a code word that satisfies this condition, but which cannot be obtained like this. Does anyone see an example? You can just use identity matrices here. Because yes, if you multiply H by identity, and so but they should be identity but of different sizes, N and M. And this is a very low, so this is not a problem for hypergraph product codes. Yes, because these identity matrices still have quite large size. But for lifted product codes, it's a huge deal, yes, because this, if we choose this matrices IN and IM, yes, then they are group algebra, so they are matrices, yes, where we have zeros and we have ones on the diagonal, but this one is an element of a group algebra and it has weight only 1. So it means that the weight of this code word is just n plus m. So it's very, very small. It's very, very small. And if group size grows, n and m, as I said, is constant. Yes, and we have a real problem. And so we cannot deal with lifted product codes as with hypergraph protocol. So we need some new ideas how to break through this counterexample. And by the way, there was also a nice paper which constructed codes differently. So they use what is called balanced product codes of bipartite graph, and they used lossless expander. But you can also define it as an instance of a lifted product code that I described it to you. And the idea is to use this construction with matrices A and B, where matrices A and B are two-sided lossless expanders. Yes, and in fact, it was shown that you can get good LDPC codes, quantum LDPC codes, using two-sided lossless expanders. But the natural thing to expect that we can use any very good lossless expander here and very good lossless expander here. But if this would be true, then this counterexample didn't work. Yes, because, for example, H is a matrix that comes from very good two-sided lossless expander. So I can give another one by transposing, and we have a problem. And exactly this counterexample explains why in that paper there was used two-sided lossless expanders which are very, very unbalanced. So it shows, in fact, this counterexample is much more severe. And so you cannot only use identity matrices. In fact, you can use any matrices. These are square matrices, yes, and you can use any invertible matrices of low weight. So if you can find for two matrices A and B, matrices U and V, that connect them like this, you have a counterexample. Yes, so U and V could be some low weight matrices. It's not necessary that they are identity matrices. So this counterexample works for all sparse matrices, which means matrices A and B cannot be sparsely connected. Yes, and this is very important to realize with the lifted product code. So you cannot use matrices. So matrices A and B kind of should feel each other, so they shouldn't be related to each other. Yes, so and that is also explains why in this construction that uses lossless expanders, they use lossless expanders of very, very different weights, because it's just not possible to use with just exactly the same. Yes. Okay. And another code that I want to describe to you is what I usually call generalized bicycle codes, but it also has different names. So it's really pity that in the quantum LDPC area we have for the same objects many different ways and many different names, and they do not match each other. So what if we use, instead of matrices A and B, just matrices that consist of one element? Yes, so we can use with this construction also such, this is just a special case. And now if we try to look at the Tanner graph of this object, then you could immediately realize, if you were in the previous lectures, the famous left-right graph. Yes, because so we have X and Z here, yes? And if we start, yes, so A is just group element. It's just the sum of group elements. And B is also sum of group elements. And then you can easily see that these boundary operators, yes, that are shown here, they exactly correspond to one skeleton of left-right complex by what is called its four-folded version. So in Dinur's paper, there was a version where we have just one instance of, so the size, the number of vertices was equal to the number of elements in the group, but here it's like it's unfolded or decorated, what is now in the very last paper, what is called decorated Cayley complex. Yes, so it has four parts, and this is exactly the same. What is interesting, so why I want to point it out, because these codes were already described before in 2014, unfortunately in unpublished work by Hastings, and he even called it left-right codes. Left-right codes. And so the Tanner graphs of left-right codes are left-right graphs. It was unpublished, but it first was mentioned in the literature in 2018 in this paper, so you can check it. But abelian case was studied even before, and of course, yes, as I said, the Kitaev-Tori code is also an example of this. You can also check this. And there were also a very famous paper by Ha and Kovalев-Pritko that studied similar codes. We also with Gleb wrote some paper in 2019 that, and this is exactly where we started with our lifted product codes. Okay, and now, so why we call it lifted product? Yes, so it's so I often asked about this. So this is related to what is a hypergraph product code? It's just a standard Cartesian product of graphs, yes? But what is a graph that corresponds to the lifted product? As it turns out, it's just a lift, yes, of the Cartesian product of two graphs. So if you want to interpret it in the graph theoretic terms, then the construction is as follows. You take the Cartesian product of graphs, And you lift it in the following way. So I show you the rule. So we on each vertical edges, we put the same labelings as in graph X, and in each horizontal, we put the same. So here is the rule, how we do it in general, yes? And what we require that these alphas and betas should be pairwise commute. And if they are pairwise commute, then what we get alpha covering of this Cartesian product of two graphs. So in some way, so we can think about lifted product as a general way. So for example, you have this problem. You have Cartesian product of two graphs, yes? And you can ask, what are L-fold coverings of this tensor product? And in fact, lifted product construction can be shown to give all possible coverings if in the product of graphs we have connected graphs. So it's, I'm not sure, so I already published this result, but yeah, this is true. So it's a universal construction for L-fold coverings for tensor product of graphs, connected graphs. And another way to describe it is to use so-called graph bundles. By the way, how many time do I have? Okay, just, yes, a couple of comments. So this is the idea of, I think it's also very important. This is the idea of twisted product. Twisted product or graph bundles. What's this? So we have, so if you remember how I defined lifts, yes, we have like graph, base graph. And we have fibers, yes? Fibers over each of the edges. And then we, for each edge, we choose some permutation and we connect them according to this permutation. Yes, if you remember, this is just a definition that we used. And fiber bundle is just a generalization of this idea, graph bundle. When all fibers are graphs, yes? So we have some edges here, and edges here. And these permutations are automorphisms of graphs. So we cannot use just arbitrary permutations, we can just use automorphism of this graph. So fiber is not a set of vertices, yes? Just a set of vertices. It is a set of vertices connected by some edges. And our permutations are restricted to be automorphism of graphs. And this phi, so this phi, it's just exactly the same. So it's a permutation that corresponds to this idea. And you can show that, in fact, this thing can also be described as a fiber bundle. And another also very interesting way how to describe it, in particular, the code that we used is a balanced product that was for graphs that was introduced in the paper by Brookman and Eberhard. And so this idea, so I don't have maybe enough time. So this is the idea of a symmetry, yes? So we have this graph and we have this graph, and all this graph has some symmetries. And we can just consider Cartesian product of these graphs, and we can just reduce some common symmetries. And there's an idea, it's much more general idea, so it can be applied to many other situations, but in this case, it also corresponds to our construction. Okay, I think maybe we can finish right here.